this video, we will discuss valence bond theory, which involves the mixing of atomic orbitals to form the orbitals that produce the shapes that we have discussed in the previous chapter. Valence bond theory is a method of understanding how various molecules are put together and how the bonds form. Up until this point, we've discussed Lewis structures, and Lewis structures are ways of predicting the types of bonds that are formed, but not necessarily why they form. And in particular, also then VSEPR theory tells us about shapes, but our understanding of atomic orbitals to this point don't necessarily correspond to all of those shapes, so we need to refine our theories a little bit. The further expansion of the idea of quantum theory or quantum mechanics can be used to understand more about the so-called valence bond theory. The crucial thing here is that electrons behave like waves, and that the electron waves or orbitals can interact with one another and produce these bonds. So the crucial thing here is valence bond theory is used to understand the bonds that are formed by combining various atomic orbitals, and how that then produces the shapes that we're dealing with. And then the other important aspect is that these bonds that are formed from the atomic orbitals, the so-called valence bonds, can never have more than 2 electrons in them. So this is a crucial aspect of valence bond theory. Perhaps the easiest example of how a bond is formed is if we look at the molecule that is formed from elemental hydrogen. Hydrogen is a diatomic element. In other words, there are 2 atoms that are bonded directly to one another. The Lewis dot structure would predict a single bond between the 2 hydrogen atoms. If you remember that an isolated hydrogen atom has a 1s orbital as its lowest energy or ground state situation, and of course hydrogen would like to have 2 electrons in its valence shell. Now, for a single atom, these electrons represent a wave, and if the 2 atoms come within close proximity to one another, those 2 waves can interact to have constructive interference. And so this is energetically optimized when the 2 electrons have opposite spin, as shown here. So they come together. There is then a constructive interference which is maximized where the 2 atomic orbitals overlap one another, which happens to be between the 2 nuclei, and this constructive interference then reinforces the wave and provides the situation where the electrons spend more time between the atoms than they do out on the opposite ends of the H2 molecule. This then produces the so-called bond that is what we describe as a sharing of electrons or a covalent bond. So in this case, we end up with an H2 molecule that has now a single orbital that is spans both of the hydrogen atoms. The 2 electrons that occupy this orbital are opposite spin, and they are a result of the overlap of the 2 atomic orbitals from the separate hydrogen atoms. So in this case then, that forms the bond. We can continue on to a slightly more complicated molecule in which we have the overlap of two atomic orbitals, but not necessarily just s orbitals. So, for example, if we consider the molecule HF, hydrogen fluoride, in the case of the hydrogen atom, the electron that is in the 1s orbital can overlap with an electron on the fluorine atom, which is in a 2p type orbital, as you can see here. And so in that case, the isolated hydrogen and fluorine atom both have one unpaired electron. If those two electrons have opposite spin, and then the two atoms come close to one another, we can have a situation where we get constructive interference, and this then produces a stable HF molecule. A further example is if we bring together two fluorine atoms to form elemental fluorine, which is diatomic. In this case, the overlap of the atomic orbitals are from a 2p orbital on each of the fluorine atoms. Where the two orbitals overlap one another, we get constructive interference, and this then produces a stable bond that is then pulling the two fluorine atoms together, and we describe this as the so-called sigma bond, or the single bond in F2.